Okay, now we are recording. Alright, Assalamualaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. Okay, so today we will continue with number system, but this time we will learn about number operations. So what we are going to learn about is that you will learn about binary number operation, okay, which all four operation, which is addition, subtraction, multiplication and division. And then for hexadecimal number operation, you will learn about addition and subtraction. Okay, and then it's gonna be just very few slides, okay, but a lot of exercises that needs to be done. Right, for binary addition, let me start with the pen. Pointer. Right. Okay, so one bit binary addition is as follows. 0 plus 0 is 0, means literally you are adding. Okay, like the normal addition, okay. And then 0 plus 1 is 1, and then 1 plus 0 is 1. Okay, but when we have extra bits, such as 1 plus 1 is basically 2. Okay, so if it's 2, means that 1 plus 1, so you will have 0, which is 2 power of 0, and then 1 is 2 power of 1. So 2 power of 1 is basically is 2. Okay, so what happened to this 1 here? Usually, if there is a number on the second position, okay, if there's a number on the second position, we will not put 1 here, but carry forward, okay, to the next position. Right, so this is the binary addition rules, okay. So 0 plus 0, 0 plus 1, 1 plus 0, and then 1 plus 1. So these binary rules, okay, you will see it later on the logic design also. Okay, now for bit binary addition, you will add individual bits and propagate the carry bits. Okay, propagate the carry bits. And to determine the sum and the carry, follow the rules in the table 1. Okay, so this is the table 1. If, okay, so for example this one, especially this one, so 1 plus 1 is basically 2. So the result of the sum is 0, the bottom one. And then the extra bit, okay, it would be the carry bit. So to determine the for example, okay, for example you have 101. Okay, so 101. So when you do addition, so 1 plus 1 is basically 2. So sum of 1 plus 1 is 0, and then carry 1. So we put a 0 here as the sum, and then carry 1 bit to the next position. Okay, to the next powerful position. So in this case, this is 2 power of 0, and then this is 2 power of 1. So we carry forward to the next power. Okay, so you only carry 1 bit. Okay, you only carry this whatever left. Okay, so as example, if we have 1 plus 1 plus 1 plus 1. Okay, so what you get is 4. So 4 in binary will become like this. So sum would be here, this bit 0. And then the carry bit will become 1, 0, which is 2. So in this case, if you want to carry forward, you will carry this 2 bit 1, 0, like that. Okay, so for this example, we only carry 1 bit here. So 1 plus 1, 1 plus 0 plus 0. So 1 plus 0 plus 0 is 1. So the sum is 1, and then 1 plus 0 is also 1. So this is binary addition. Okay, so what if we carry forward and then until there is no digit to be added? So for example, on these questions, 1011 plus 0110. Okay, so when you try to add it, okay, so 1 plus 0 is 1. 1 plus 1 is 2. So 0, carry forward 1. So 1 plus 1 is 2, carry forward 1 again. And then 1 plus 1 is 2 again. Carry forward 1 bit. So there's no more to add. So we just pull down the carry forward bit. So you will get a 5-digit binary. Okay, and then also the same example. Okay, 1111 plus 1111. So this is base 2, eh? So this is base 2, base 2, base 2. Don't forget that. Okay, now, so 1 plus 1 is 0. Okay, 0 carry forward 1. So now we have 1 plus 1 plus 1, which is 3. So 3 means, okay, 3, sum is 1, carry bit is 1. So 1 here, carry bit 1 here. So the same things, 1 plus 1 plus 1, which is 3. So 1 here, carry forward 1 here. And then 1 plus 1 plus 1 is 3 again. So 1 and then carry forward. So since there's no digit to add, so 1 is the end result of the leftmost bit. So what we get is 1110, 11110 as the end result. Right, for binary subtraction, follow the table here. Alamak, sorry, table. Okay, so table 2 binary subtraction rules. Okay, so we have column borrow and then column sum. So let's say this is a 1 digit of subtraction rule. So 0 minus 0 is sum is 0 and then no borrows. And then 0 minus 0, 0 minus 1. So 0 minus 1. So 0 minus 1. So we assume there's a bit before that. So we borrow. So when we borrow, 1, 0, not 10, 1, 0 minus 1. Okay, so 1, 0 is 2 in decimal. So 2 minus 1 is 1. So your sum is 1. Your borrow bit will become 2. 1, 0. Okay, and then 1 minus 0 is sum is 1, no borrow. And then 1 minus 1, sum is 0, no borrow. Okay, so that is for binary subtraction. So for binary subtraction, subtract the individual bit and borrow if needed. If the value at the top is not enough to subtract with the value at the bottom, so you need to borrow. Okay, so if needed to. Okay, so to determine the sum and the borrow, follow the rules in table 2. Okay, so when you borrow, it will become 10 base 2, which is 2 in decimal. Right. So this is example. First one is a very simple one. 1111 minus 1. So which is 0001. So when you subtract, 1 minus 1 is 0. Then 1 minus 0 is 1. 1 minus 0 is 1. And then 1 minus 0 is 1. Okay. So that's why when you do the calculation for the IP addressing, this is a 15. Okay. And then when you want to get what is the previous address, so you can just minus 1. So in here, if you look at this, 1111 minus 1 is 1110. Okay, so and then for second example, this one is also straightforward, okay, but needs to be borrowed. So if you look here, 1011 subtract 110. So the rightmost bit, so 1 minus 0 is 1. 1 minus 1 is 0. But this one, 0 minus 1 cannot be subtracted. So they borrow to the previous bit here, which is 1. So 1 here will be cancelled out, become 0. And then the digit that is borrowing, okay, that digit become 1 0. So there's no more 0 here, it become 1 0. Okay, so you will write it like this, 1 0. So 0 becomes 1 0 after borrow from the front. So 1 0 minus 1, okay, is 1. So 2 minus 1 is basically 1. So you will write 1 as the sum, as the result. And then 0 minus 0 is 0. So this is your answer, 101. Okay, base, don't forget, base 2. Okay, and then this is another example where you need to borrow. Okay, you need to borrow also. So 1, 0, 0, 0, and then minus 1. So in your mind, you know this is 8, and then minus 1 is basically you will get 7, right? Okay, so how do we get that? 1, 0, 0, 0, 0 cannot subtract 1. So they need to borrow to the front. But the front also have a 0. So they borrow again to the front. So this time is also 0. Then they borrow to the front again. Then they found 1 there. So if it's 1, so what they do is that they will borrow 1 here. This will become 0. So this one, okay, the next one will become 1, 0. Actually, it become 1, 0. And then since the next digit is also borrowing this digit, so what happened is 2, when 2 is borrowed, okay, so they will minus 1. So they will minus 1, right? So 2, if minus 1 will become 1 here, so they will borrow it here like this. And then if it's borrowed again, because of the last digit here needs to borrow again. So what happened is that they cancel the 0, then they will become 1. And then next, so the last digit that needs to borrow is the last one. So 1, 0. So this one become 1, 0. So 1, 0 minus 1, 2 minus 1 is 1. Okay, and then 1 minus 0 is 1. 1 minus 0 is 1. And then 0 minus 0 is 0. So in this case, your result is 1, 1, 1 base 2. Okay, so that's how you will get the, how you borrow. Okay, how you borrow the bit. This is also another questions asked in the IP addressing when you are doing a subtraction actually. So if the bits start at 16, okay, so 16 minus 1 is basically 15. So what is the binary number for 16? 1, 1, 2, 3, 4. Okay, so when you try to minus all of it, when you try to minus 1, okay, so you need to borrow. So what it means is that from 1, 0, 0, 0, 5 bits minus 1, so basically it will become 4 bits all 1. Okay, so do that exercise, do this exercise, this kind of exercise where you need to borrow. Okay, next. Two's complement. Okay, remember when I teach you about the two's complement, right? So two's complement number is a way to represent a negative binary numbers. Okay, so technique to create two's complement for a number is to invert each bit. 1 becomes 0 and then 0 becomes 1. Right? So this will become first complement. And then, okay, so from first complement, you will add 1 to the result, of the first complement. Then this will become two's complement. Okay, so for example, what is the two's complement for 1, 0, 1, 0? So here, is it doesn't mention, right? So it doesn't mention what is the value for the what is the value, or is this a number? Is this number is a negative or positive number? Right? So what is given here is that 1010, which will be invert each bit, okay, to become 1's complement, 0101. And when we add it plus 1, so you will get 0110. So which in this case, this is a 2's complement for positive 6. Okay, so you might get confused with this type of style. Okay, so usually I would mention that we have a system number of 8 bits, and then given a number, okay, given a decimal numbers, for example 13, okay, so positive 13 or negative 13. So what is the 2's complement of the negative 13? Or maybe what is the 2's complement for positive 10? Just like that, right? So that is how you want to do the 2's complement. This one is quite confusing for you. So just follow the lab. Okay, just follow the lab tutorial. So it must be given with the size. Okay, it must be given with the size. Don't use this type of style. So let's say, what is the 2's complement for 10? Okay, positive 10. So what you will do is 10, 10. So but basically this is wrong. 2's complement must have a sign bit. So when you represent it like this, okay, 10, right? So 10 and then 10, 10. But this is a 10. But you want to tell that this is a positive 10. But is this a positive 10? No. If it's a 2's complement, it must be 0 at the front of it. Okay, it must be 0 at the front of it. So quite confusing if you're following this. Okay, so just follow the one that I have teach you. Okay, so just follow the one that I have teach you. So put a 0 already. Okay, put a 0 already. So to show that this is a positive number. And then if I say, okay, so change it to negative 10. Then use the first complement. Just use the first complement. 1, 1, 1, 1, 0, 1, 0, 1. Okay, so this is the first complement for negative 10. And then you want to get the 2's complement plus 1. So you will have 0, carry forward 1, and then this is 1, this is 1, this is 0, this is 1, this is 1, this is 1, this is 1. So you will get a 2's complement of negative 10. So this is the correct answer. Okay, so not so confusing. So this is much easier for you to understand. Don't follow this, okay? Okay, then okay, using 2's complement. Okay, so once you need to subtract a number by another number, it's also the same by adding a number by a negative number. So in binary, to subtract a number by another number is the same with to add a number by 2's complement number. So the procedure is to make sure that the minor end and the subtrahend have the same number of bits. Okay, so in our case, I would say that, okay, so use the same system. If it's an 8-bit, then use an 8-bit. But if the value exceed, then use 16 bits. Okay, and then increase again, 32 bits. Okay, but for the sake of questions, when you try to answer the midterm, usually it doesn't exceed until 32. So because it is too long. Okay, it is too long. Okay. But the computer, okay, but our computer, if you look at the, alright, yeah, here. When you right click this PC, and then when you look at the system here, it will see that this is a 64-bit, right? So if it's a 64 bits, it means that the system number that they use is 64. Okay, because of they want to support with the higher end computation and to shorten the time, okay, to complete the execution. So that's why they use a 64-bit. But for our study, it's only exceed until 8 to 16 bits only, right? And then now, so make sure the size of the bit must be the same. Okay, if it's either 8 or 16. And then change the subtrahend to its 2's complement number. Okay, so make sure first is that when you have a number and then you will get 0, 0, 0, 1, 0, 1, 0 like that. So you make it complete 8 bits. And then change the subtrahend to its 2's complement number. No. It should be 1's complement number. Okay, so 1's complement number is you flip the bit. Okay, you flip the bits and then plus 1. Okay, then plus 1. Once you flip the bit and then plus 1, then you will get your 2's complement, right? So then once you have the 2's complement, then you can add another numbers that is a positive numbers. So and then once you get the result, if it's exceed from the size of the original size, so let's say we have 8 and then it exceed more than 8, which is a 9 bit, then discard the leftmost bit, okay, or the most significant bit, which is the 9th bit. Okay, so we will discard that and then we just take out the original size result as the result. Okay, so again, this one used to complement to solve 1011. Okay, so in this case 110 need to be converted into 2's complement. Okay, so the minor end is 1011, which is the 4 bits, and the subtrahend is 110, which is the 3 bits. So make 110 to become 4 bits. So 0110 and then invert. Okay, and then invert 0110 become 1001 and then plus 1 it will become 1010, and then when they try to add, okay, so you will get an extra bits. You will get an extra bits. Okay, so when you add extra bits, okay, remove it and then you will get 0101. So which is the end result will be 5. Okay, so 5. So actually this one is 11. 11 minus 6 is basically 5. Like that. Right. So this is for 2's complement again. So to solve the following problem, 1111 minus 1 is equal to if we 2's complement, okay, so 0001, if you change or convert to 2's complement, you will get 1111. So when you try to add it, you will get 1110. Okay, 1110, and then the first bit here or the leftmost bit here, okay, will be discarded. So you will get 1110. Okay, so for 10001 minus 1, and then you 2's complement, okay, so you will get 1111, and then you don't have a problem of borrowing the bits, you just add it. So the result is that you will get 10 and then 111. So the leftmost bit here will be discarded. So the result is 0111, which is 7 in this case on the decimal. Right. So that is for binary subtraction. For binary multiplication, for simplified version, this is for 1 bit of binary multiplication. 0 multiplied by 0 is 0, 0 multiplied by 1 is 0, and then 1 multiplied by 0 is 0, and then 1 multiplied by 1 is 1. If you look it like this, okay, multiplication is basically the same logic of AND logic, right? Okay, so it's the same truth table for AND logic. So basically, for binary multiplication, it needs all bit become 1 to get the result of 1, right? And then, so this is an example. Okay, so it's when you do the binary multiplication, it will be longer. Okay, it will be longer. You need space. So 1010 times 11, and then when you try to multiply, it will become 1010, and then you will add it. So you will get 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1, and then 1. So this is the answer. 11110. So that is for your binary multiplication. And then if we need to multiply 1010, 1 time multiply by 101. Okay, so what you will get is 1010. And then the middle bit is 0, right? And then continue with another bit 1. So we can, when we multiply, we will get 1010. So here, sum all the results. 0 and then 1 and then 0 again, and then 1 plus 1 is 2. So 0 carry forward 1. So 1 and then 1 again. So this is the result of the multiplication. Easy, right? Because of binary only consists if it's either 0 or 1. So that's it doesn't exceed more than that. So it's quite easy to do the operation. Okay, but for the division, okay, binary division follows the same procedure as decimal division. For example, if we have should be 1110. Okay. So here should be 11110. Okay. So divide by 3. Okay, 3 in decimal. So which is in binary it is 11. So when you try to divide by 11, so means that we need to take 2 digits. So 11 divided by 11, so you will get 1 here times 11. So you will get 0, 0. And then pull down another bit, 0, 1. So 0, 1 divided by 1, 1 is basically 0 again. So you will get 0, 0. And then pull down again. Okay, sorry. Minus first. So 1 minus 0, you will get 1. So now you have 1 bit and then you need an extra bit to divide it. So pull down again another bit. So 1, 1. Divide by 1, 1. So you will get 1 here. So 1 times 1, 1. You will get 0. And then pull down the bit 0 here. So since it is all 0. So you don't need to divide it. So you just put 0. Okay. So the answer is 1010 base 2. So this is for binary division. Okay, so next is the hexadecimal addition. So for hexadecimal addition, we also follow the same procedure with the decimal addition, except the rule for carry. If the sum number is greater than 15, so the amount will carry a 1 to the next column. So for example, this is 15 base 16 and then 9 base 16. So we need to add. So when you try to add, you look at it, it looks like the same as decimal, right? But you need to remember, the result and the carry forward, there's a rule, certain rules that you need to follow. For example, okay, place it in, vertically. And then 1, 5, and then 0, 9. So 5 times plus 9 is 14, right? So now we have 14 here, but 14 can be written as the result. So you need to represent it into hexadecimal. Okay, so this 14 is on your mind is a decimal actually. Okay, it's a decimal. So when you add it, okay, you add like a decimal. So 5 plus 9 is 14, which is 14 in decimal is convert to hexadecimal, which is E. You will write it as E. So if I was like you, I would just write it like this, plus 9. So 5 plus 9 is 14. Okay, 14, which is E. And then, so do we need to carry forward? No. Okay, you don't need to carry forward. So you just add it as usual. So 1 plus 0 is 1. So when you combine, you will get 1e base 16. Like that. Right. So what about more than 1 digits, more than 2 digits? So what we have here is 2f8 plus 38. So when you add 8 here, okay, when you try to add that, the value exceed more than 15, more than 15 means that you will get a result of 2 digits. So in this case, 8 plus 8 is basically 16. So let me write somewhere. Let me show it on the paint. Here's my pen. Oh, okay. Okay, now 2f8 38. So 2f, okay, 2f8 and then 38. Okay, 38. Write this as 16 so that you will remember this is still hexadecimal. Okay, but when you try to add, you will add like a decimal. Okay, but because of your thinking is always on the decimal side. So 8 plus 8 here is 16. So 16. So it is 2 digit, and then you try. First is that you try to subtract to a 16 base number. Okay, so first is minus 16, and then if it's not minus 32, 16 minus 2 times 2 is 32, and then 32 16 times 3 is 48, like that. So all the numbers in 16 multiplication. Okay, so 8 plus 8 is 16. So try to subtract if it's equal to 16 or more than that. So if it's more than 16 or equal to 16, then you can subtract to 16, and then you will get 0, right? So you will get 0 as your sum. Okay, you will get 0 as your sum. So this would become 16 power of 1. So 1 here will be carried forward to the next bit. Okay, 1 here will be carried forward as the next bit. So 1 plus f plus 3. So your mind will try to add, okay, f is 15. Okay, I will try put in a bracket so to tell myself, oh, okay, this is the decimal, so I will add 1 plus 15 is 16, 16 plus 3 is 19. Okay, you will get 19. And then minus 16 again, so you will get 3 this time. Okay, so here is 16 power of 1 again, so you will carry forward 1 here. So 1 plus 2 is 3. So 3 here is nothing, that is only 1 digit. So what you do is you combine it. So 3, 3, 0, place 16. So did you get it? Did you get for these questions for the hexadecimal? If not, we will do an extra exercise for that. Just an exercise. So for you to do this, for you to do the calculation. Before we do the subtraction, because even if you make a mistake in subtraction, addition, then you won't be able to know about your subtraction. So let's say we do the exercise in the lab. Okay, the questions in the lab is number operation, right. Yes, 1 questions. Now let me use the example in, where's my paint? Yes, this one. Okay, so let me Control A, T. So let me use the sample on lab 3 actually. It is hexadecimal addition on page 42. Okay, so it is on page 42. So the question is example 3.5C. So this is C, D. I'll write it, make a gap on it. So DF. Okay, so DF base 16, and then plus AC. So don't worry. For addition, you will have a problem, but subtraction will be a little bit harder. But just practice with the 2 digits of hexadecimal first. Then, on the lab tutorial, so they use the division here, okay, to separate it. Okay, they will use the division to separate it, and then like this. Okay, now, okay, so this is, hexadecimal numbers, right? So what I did is that I will write it like this, 15. What about this? This is 12. I remember this is 12. This is 13. So C is 12. This will be 13. This will be 10. Okay, now. Okay, so what do you need to do? And then you just need to add it as usual. Okay, you just add it as usual. F plus C is basically 15 plus 12. So 15 plus 12 is 27. This is 27. Okay, so 27 you minus 16. Okay, so you will minus 16. So basically 16 is 7 minus 1 is 1, 2 minus 1 is 1. So what you will get is 11 for the sum, for the sum or the result. And then the carry bit, okay, so the carry bit is 16. Sorry. Yeah, okay. So 16 power of 1. Okay, this one, So 16 power of 1. And then for B here, okay, we convert to, 1 here is convert to hexadecimal. A is 10, so 11 will be B. Okay, so here you will write B here. Okay, so I will write it as a B here, or maybe, hold on. I will write it like this. Okay, arrow. I will put in an arrow here. Convert 11 to hexadecimal, so it will become B16 here. Okay, next. So what about this one? You will carry forward 1. So 1 plus D plus A. So 1 plus 13 plus 10. Okay, so 1 plus 13 plus 10 is basically 14 plus 10 is 1 plus 13 plus 10 is basically 24. Sorry. 24. Okay, so now we get 24. So 24 is bigger than 16, right? So you minus 16. So you will get 8 here. Okay, so this is 16 power of 1. Okay, so this is 16 power of 1. So do we need to carry forward? Yes, you need to carry forward 1 here. And then for the result, do we need to convert anything? No. So 8 is still 1 digit. So here 1 plus 0 is basically 1. So we put it down 1 here. So when you combine, you will get 1, 8, B base 16. Okay, so that is for addition. Okay, so to do the addition with the carry forward bits. Okay, so if you don't understand, just interrupt me. Okay, now next, subtraction. Okay, so first for subtraction, we need to change the subtraction form into addition with negative number. Okay, so first, convert the subtrahend to binary number. Make sure that the minor n and subtrahend have the same number of bits. And then change into 2's complement number. And then convert the result to hexadecimal number back again. And then, okay, you add the minor n with the result. And then discard the carry, which is the first digit. Okay, for example, we have 238 minus F4. So first is that the minor n 238 is a positive number. And then the subtrahend is F4, which needs to be subtracted, right? So F4 is changed to binary numbers. Okay, will be changed to binary numbers. And then convert the subtrahend to binary, which is 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0. Okay, so the 0 here is to show that this is a positive number. So then we want to convert into 2's complement, that it will become a negative number. So change the subtrahend into its 2's complement number. So you will get 1, 1, 1, 1, 1, 1, 0, 0, 0, and then 0, sorry, so 0, 0, 0, 0. 1, 1, 1, 1. Let's do it from the start. Okay, just like this. And then change it to first complement. Like this. Plus 1. So you will get 0, 0, 1, 1, 0, 0, 0, 0. 1, 1, 1, 1. Okay, so this is your 2's complement for F4. Okay, for F4. So convert the result into hexadecimal. So to convert into hexadecimal, it will become F0 C. Okay, F0C base 16. And then next would be you will add it. So you will add as usual as a hexadecimal addition. So 8 plus C, which is this is 12, right? So 8 plus 12 is 20. So 20 minus 16 is 4. So 4 here. This one is 1. So carry forward 1. So 1 plus 3 is 4. And then 2 plus F, this is 15. So 2 plus 15 is 17. So 17 minus 16 is 1. Okay, so carry forward 1. Okay, carry forward 1. So 1 and then carry forward 1. So you will get 1 here. So since when we do the addition in the 3 digits, so they will remove it. This will be discard. They will discard the first digit. So what you have as the result is 1, 4, 4. Don't forget, base 16. Okay, so that is how they do the hexadecimal subtraction. Okay, so you might want to ask, can I use the borrow bits? Yes, you can, but quite complicated. Okay, quite complicated because of and then what's the questions? 238 minus F4. Let's see. 2, 3, 8 minus F4. So imagine that you want to borrow it because this one is 2 digit and then you want to borrow the previous one. Okay, so what you need to do is you just subtract as usual if the number can be subtracted. 8 minus 4 is 4 here. Now, 3 minus F is not enough, so you want to borrow here. So when you try to borrow this one, okay, so this become 2. 2 minus 1 will become 1. When they go to the one that needs to borrow, 1 here will change into 16. Okay, 1 here will change into 16 because my mind always think about the decimal, right? So this one will become 16. Or if you want to represent into hexadecimal numbers, right? It will be complicated. So your mind still need to think that this is decimal. So 1, 6. Okay, so 1 here, if it's borrowed, it will become 16. So 16 plus 3 in decimal. Okay, and then this become 15, right? So 16 plus 3 is 19. Okay, 19 plus minus 15. Okay, so 19 minus 15. You will get 4 here. Okay, and then 1 here has been borrowed. So what's left is 1. So 1 minus 0 is 1. So your answer is 1, 4, 4 base 16. Okay, so it depends on you. Okay, it depends on you. But if the question asks you to do hexadecimal subtraction using 2's complement, then just do the 2's complement. Okay, it's because of using a 2's complement, F4, okay, can be changed to a binary numbers. Okay, you can just change it using a binary numbers and then change to a 2's complement, and then once you do the 2's complement and then change it back to the hexadecimal. So it's basically the same style. Okay, so that one is much more easier for you, and then you will not do any mistakes. Rather than you are using like this, borrowing, and then you need to think, okay, so this is this is decimal. This is 16 decimal, and then plus 3, which is can be a decimal too. But this one F is hexadecimal, so you need to convert back to decimal. So 16 plus 3 is 19, and then 19 minus 15 is 4. So a lot of thinking. Okay, so it depends on you. Okay, it's up to you on how you want to do the exercise. Okay, because of the questions. Oh, because on the lab they have a certain questions that let me show you the lab exercise. Okay, now we are finished. We already finished our class. Okay, so what's the module? Yeah, this one. Right, no question, eh? Okay, very good. Okay, by the time when you try to answer your question and then, you made a mistake. And then, you made a, what kind of question, what kind of computation that you did? So cannot help it because we are doing it in the online session. So I may not be able to check. Okay, when you are doing it right now. So I hope that by week 4 you can get back, because I thought that they said that students can go back to the hostel on week 4. I think this week. So just come back here. It will be easier for you to study face to face. Okay, trust me. Face to face is much more easier to learn. Okay, so hexadecimal number operation. No, not this one, not this one. The question. Yeah, you will do the questions with the fractions, and then I cannot see any WhatsApp, sorry. So there we have a multiplication. I did not teach you, right, for the multiplication. Right, okay. So for the binary multiplication, it's basically the same. But for the hexadecimal, okay, so when I did not teach you, it's basically because you can just change this hexadecimal number to become a binary number and then do the multiplication. So although this will become 4 times 3 hexadecimal will become 12 digits of binary numbers, but it is much more easier for you to do this exercise if you convert it using binary numbers. Also the same for the division. Okay, for the division for hexadecimal number, ABCD divide by DE. Okay, so there's no shortcut. Okay, the easier to do is that you convert it ABC here to become a binary numbers, and then you do the division. Okay, so that is for the number operation. So if you ask me why do we not do the decimal operation, it's because it's very easy for you. So the thing is that we need to do the operation that is done by the computers. Okay, so that is how the computer do. Okay, so subtract will use the 2's complement. Okay, and then this part actually I need to teach you. Okay, so remember when you type in your keyboard, so how does the computer understand it? Okay, how does the computer understand it? You type word. Okay, when you type word, for example, table 3, 4. So when you are transferring the bits, okay, when you are transferring the words there, T there. So how does the computer, oh sorry, here, pay RM 100.00. Okay, excluding the, what is quote. Excluding the quote, just concentrate on the, word here, pay 100, RM 100 ringgit with a dot here. So how does the computer understand it? So they translate using the ASCII keyboard encoder. We call it the ASCII code. Okay. Sorry, ASCII code is a representation for each of the key on your keyboard. Okay, space here is a space bar, can be represented by the ASCII 0100000. Okay, so let's say you type P. So look at the P here. The P here. So this one, 1010000. But you need to remember, even though we have a lot of keyboard here, but this one is only a portion of it. So when you want to look for a full ASCII table, then you can just Google. Look at the ASCII table. Actually, it's not only caps lock, but it's also have a small caps. okay, small caps character. So let's say if I type like this, PAY, just like this. So how do we convert into an ASCII code? Okay, so look at the table here. This is a P, and then for A, so what is the A? This one, 1000001, and then Y, where is Y? So here, 1011001. Okay, so that is how they convert it. Okay, they will convert it into ASCII code. So, so is it important? Is it important to you to use this ASCII code? Yes, when you do the coding, when you try to do the coding, the back end of the engine or the back end of the coding, okay, you need to recognize a character. So this character must be recognized, and then usually when they are read from the keyboard itself, okay, so when you try to run the coding in assembly, so what they do is that they can recognize the ASCII code here. So when you just type, let's say I type 1001011, the assembler will encode it to become K, or vice versa. Okay, so or the other way, just like that. So this okay, this is only for hardware-based coding. Okay, hardware-based coding. So that's the end of our session. Okay, so is there any other questions, or you want me to ask you questions? Cancel. Okay, that's okay. So we will do the exercise on lab. So I will let you. We will end the session today. Okay. So we will end the session. Those who do not understand, then you can go back to the slides and then look at the notes and also from the video. So that's all. I'll see you next week. Okay. Assalamualaikum and bye-bye.
Bye-bye.
Salam.
Thank you, madam.
Thank you,
Thank you,
madam.
madam.
Thank you, madam.
Thank you, madam. Thank you, madam.